Welcome you all. Today we are going to discuss one more problem in combustion and fuel, or this problem we can consider as the exercise in a gaseous fuel for alternative fuel. It states that a dual fuel engine operates by aspirating a mixture of air and fuel, which is then ignited by spontaneous ignition of small quantity of diesel fuel injected near the end of the compression stroke. A dual fuel engine is operating with a gravimetric air-fuel ratio of 20 and the effective atomic hydrogen to carbon composition of the fuel is 3.1:1. Write down the stoichiometric and actual combustion equations and calculate the volumetric wet gas composition. Second, if the calorific value of the fuel is 46 megajoule per kg, what percentage of this could be recovered by cooling in the exhaust gas from 627 degrees centigrade to 77 degrees centigrade? If the fuel consists of methane CH4 and cetane C16H34, what is the ratio of two fuel mass flow rates? Now, first we have to write the given data. This is a dual fuel engine, air and fuel mixture admitted to the engine. The combustion is initiated by the pilot quantity of fuel, that is diesel. If air fuel ratio is equal to 20:1 gravimetric and the hydrogen to carbon composition is 3.1:1, find the stoichiometric and the actual combustion equations and calculate the volumetric wet gas composition. So we assume this is 1A, 1B and this is 1C. If the calorific value of the fuel is 46 megajoule per kg, what percentage this could be recovered by cooling exhaust gases from 627 degrees centigrade to 77 degrees centigrade. So this 627 is equal to 900 Kelvin and 77 is equal to 350 Kelvin. If the fuel consists of methane CH4 and cetane C16H34, what is the ratio of two fuel mass flow rate? Solution: they given hydrogen to carbon ratio is equal to 3.1:1, so that the molecular formula of the fuel will be CH3.1, assuming Y kilomole of O2 plus 3.76 N2, that is air, is produced 1 kilomole of CO2, then 3.1/2, that is 1.55 kilomole of H2O, Y multiplied by 3.76 kilomole of N2. Now, for a fuel CH3.1, the stoichiometric air fuel requirement is 1 plus 3.1 divided by 4, that is A plus B by 4 minus D by 2 minus 0 by 2, that is equal to 1.775. So the stoichiometric combustion equation becomes CH3.1 1.775 O2 plus 3.76 N2. It will be producing 1 kilomole of CO2, 1.55 kilomole of H2O, then 1.775 multiplied by 3.76, that is 6.674 kilomole of N2. This is answer 1A. Now, the air fuel ratio is given. The gravimetric air fuel ratio is equal to 20:1. That means 20 kg of air required per kg of CH3.1. Therefore, on kilomole basis, 20 divided by number of moles of air, oxygen and nitrogen, that is 4.76 multiplied by 29 divided by 1 kilomole of fuel, 12 plus 3.1. So we get 0.1448 divided by 0.066. We get 2.1877, that is 2.19. Air fuel ratio on molar basis is equal to 2.19 kilomole of air per kilomole of fuel. Now the actual combustion equation becomes CH3.1 2.19 O2 plus 3.76 N2 produces 1 kilomole of CO2, 1.55 kilomole of H2O, then 2.19 multiplied by 3.76, 8.234 N2, and here the excess O2 is available, so in the product the O2 will be present. The amount of O2 in the product is equal to 2.19 minus 1.8775, that is equal to 0.415 kilomole of O2. So this is answer 1B. So the next question is volumetric gas composition. So for that, we have to find out the summation of the product is equal to 1 plus 1.55 plus 8.234 plus 0.415 get 11.195 kilomoles. The composition of the products CO2 is equal to 1 divided by 11.195 multiplied by 100, that is equal to 8.93 percentage. Then H2O 1.55 divided by 11.195 multiplied by 100, we get 13.845 percentage. Then N2 8.23 over 11.195 multiplied by 100, we get 73.515 percentage. Then for O2 0.415 over 11.195 multiplied by 100, we get 3.71 percentage. This is answer 1C. Now the second question is, if the product of combustion is cooled from 627 degree to 77 degrees centigrade, what could be the percentage of heat can be recovered? Now assuming that the exhaust gas from the engine at 627 degrees centigrade is passing through an heat exchanger where it transfers the heat to the surrounding and the product will be the 350 Kelvin. So with this amount of heat liberated from the product cooled from 900 Kelvin to 350 Kelvin, what would be the percentage of heat we can be recovered? First we will apply the steady flow energy equation, that is H of 900 Kelvin plus Q is equal to H of 350 Kelvin plus W, and neglecting the kinetic energy and potential energy. The system is heat exchanger, work is not given and assumed it is 0, so that we can say that Q is equal to enthalpy of 350 Kelvin minus enthalpy of 900 Kelvin, assuming it is equation. Now enthalpy at 350 Kelvin is equal to sigma of N of I into H of I. This N of I is the moles of the exhaust products, and then H of I is the corresponding enthalpies. Now from the table, this molar enthalpy they given with respect to the temperature. For 300 and 400 they given. So 350 is the average between 300 and 400. So for 350, CO2 is equal to minus 391.476. For H2O minus 240.066. For N2 plus 1.511. For O2 plus 1.541. Now we have to find the enthalpy at 350 degrees centigrade is equal to, for mole of CO2 is 1, mole of H2O is 1.55, mole of N2 8.23, for O2 0.415. Then at 350 Kelvin is equal to minus 391.476, for H2O minus 240.066, for N2 1.511, for O2 1.541 multiplied by corresponding kilomoles, we can get for CO2 minus 391.476, for H2O minus 372.102, for N2 12.435, for O2 0.639, and then this summation is equal to minus 750.50 megajoule. Then for 900 Kelvin, minus 365.477 minus 219.899, for N2 18.219, for O2 19.244. Then multiplied by corresponding moles, we can get minus 365.477 here, minus 340.843, 149.942, for O2 7.986. Then this summation is equal to minus 548.39 megajoule. Now apply these two values in equation 1, that is Q is equal to minus 750.50 minus of minus 548.39, that is equal to minus 202.108 megajoule. this negative sign is heat is transferred from the system. Now, this heat is transferred in a heat exchanger where the temperature is decreased from 627 to 77 degrees centigrade. Now, heat recovery from the combustion of fuel is equal to this Q over mass into calorific value of the fuel. Then calorific value of the fuel they given, that is 46 megajoule per kg. We have to find out this mass of the fuel. This mass of the fuel we can be obtained from the fuel molecular formula is CH 3.1. That is 12 plus 3.1, that is 15.1 kg of fuel. So that percentage of heat recovery is equal to 202.108 over mass of the fuel 15.1 multiplied by 46, that is megajoule, then kg megajoule per kg. So we can get 29.1% answer 2. Now the third one is if the fuels are methane and cetane, C16 H34. So we have to find out ratio of flow rate. Now assume X kilomole of CH4 mixed with C16 H34 produces X plus 16 of CH3.1, that is given. Now making a hydrogen balance, we get X plus 16 is equal to 4X plus 34 is equal to X plus 16 multiplied by 3.1, that is equal to 4X plus 34 is equal to 3.1X plus 49.6. While simplifying, we get 0.9X is equal to 49.6 minus 34. 0.9X is equal to 15.6, then X equal to 17.33 kilomole. Therefore, the ratio of two fuels are 17.33 CH4 is to 1 kilomole of C16H34, that is cetane. Then 17.33 multiplied by 12 plus 4 is to 1 multiplied by 16 into 12 plus 34, that is 17.33 multiplied by 16 is to 226 multiplied by 1. Now the ratio is 277.28 over 226. It means that 1.227 kg of methane mixed with 1 kg of cetane. So the ratio is equal to 1.227 is to 1. Answer 3. Thank you.
Subscribe to our channel, like if you're satisfied, and share because it may be useful to someone.